Good morning, JavaSummitIL. I'm very, very excited being here and also very happy, but I'm also a bit sad because on this stage we should have had Deepu K. Shashidran, who, due to unfortunate bureaucratic circumstances, could not be here. Instead of him, you are stuck with me. And this is a keynote talk. I prefer calling it an opening session talk. And for that, you need an excellent topic. So how do you create an excellent topic? I'm going to talk about Project Loom, but to make it excellent, I'm going to add several things. First, I'm going to add a quote from one of your favorite TV series or movies. Then, in order to make it even better, you mix in a meaningless sentence, like what's in it to me, or demystified. And to make it perfect, to the first slide, you add an AI-generated picture. That's what we do today. This picture was generated by DALL-E with prompt of spaceship and enterprise and Loom and Van Gogh style, okay? So, are we ready to go? I'm Haim, and I've been doing software development since I was 13 years old as a hobby. My first production server was a Commodore 64, and I discovered that it's a very profitable hobby, so I've been doing this professionally for more than 30 years. During this journey, I've been doing software development, architecture, engineering management, and even had the experience of having 8 years in my life doing consulting as an independent performance expert, solving concurrency issues, garbage collection problem, and improving service performance and scalability. I'm one of the organizers of Java.IL and Java Champion. In the last 6.5 years, I've been working in Next Insurance, starting as the first development, and then through various engineering management roles, I've helped building the engineering organization of Next Insurance. In Next Insurance, we develop in Kotlin, so all of the examples in the talk today are going to be in Kotlin. In addition, I am married, I have 2 daughters and a dog that is named after the sidekick dragon from the movie Mulan. The first one, not the second one when they ruin it all. So let's start. Today we are going to get an introduction about Project Loom. A loom in Hebrew is nula riga, and it is used to weave threads into a fabric, which is a very excellent name for this project. And it is a massive project that has been taking place for over 5 years with the project leaders Ron Pressler and Ellen Bateman. It consists of several Java enhancement proposals, JEP 425, 428, and 429. We're going to discuss the first 2 in this talk. So, if you're a Go enthusiast and writing Go, at a certain point in the talk, you're going to say, wow, but that's really like what we have in Go. So, I acknowledge that. Let's move on. So let's start by talking about concurrency. Suppose you have a server and you want to handle a request. And for example, let's think that you want to get a bid for a price for some kind of a product for a certain user. And this task has a start time and an end time and a duration, which also called the latency of the task. And during the life cycle of this task or request, it is going to be spending its time in 2 different states. The first one is running when you consume CPU and actually using it. And the second one is blocked, usually waiting for I/O. So, our task or request is going to alternate between these 2 states. Certain time it's going to do nothing, and certain times it's going to consume the CPU. For example, at the beginning it resolves the country of the user, and then it goes to 2 different servers in order to get the bid. Usually it will be more than 2, but for our example it is 2. As you can see, this is very aligned with the Java programming style of linear development. Like you'd have thread per request development. So first you go and find the user country by email. Then you go and get a bid from the server A and from the server B, and then you calculate something between these two results. This is very simple, very straightforward way of programming. However, you probably also know that you can do things concurrently. So probably you can go and reach server 1 and service 2 together. And this complicates things. And in addition, you probably want to handle more than one request. You want to get a bid for John and the bid for Rob. And without noticing it, we just introduced concurrency into our system. And when I mention concurrency, a lot of things pop into your head, like race condition and callbacks and cache coherence and thread pools and immutability and threads and channels and deadlocks, and you name it. And if you didn't get headache now, you will probably get headache later, because concurrency is hard. And Java actually has multi-threading, concurrency, and parallelism baked into the platform from its first version. Java 1.0 already had threads and notify and wait and synchronized. In Java 1.4, non-blocking I/O was introduced with socket channel and selectors. And while it seems not really related to concurrency, this is what enables a Java platform server be highly scalable. In Java 1.5, Java.IL concurrent was introduced with executors and futures and reentrant locks and semaphores and latches and a lot of other constructs that was very useful and capable. In Java 1.7, parallelism was tackled with the fork join pool, and in Java 8, with all the closures and streams, parallel streams were introduced and completable future. 8 years later, in Java 19, Project Loom is introduced with virtual threads and structured concurrency. So if you look on the traditional Java concurrency model, it uses a style that is called thread per request style. We saw it in the code example before, which means that every unit of concurrency requires a thread that is a Java thread, which also an OS thread, and sometimes you need even more than one of these. You usually don't create them manually. You use executors and thread pools in order to utilize them and reuse them, because they are quite expensive and a very expensive resource. So if we go back to our example, how will it look like? First of all, we find the user by email. That's exactly as before, but then we need some kind of concurrency, so we submit task into an executor. In here we use a method called invokeAny. And invokeAny gets a list of callables, and eventually it picks one of them and returns the price of the best bid. Please note that under the hood, there are 3 threads involved in this mechanism, okay? Now let's talk about scalability and hardware utilization. We have a machine either in your garage or in your near-to-house cloud provider, like Amazon or Google. It's very expensive. And what we want to do is to get to a situation when we are able to utilize its most precious resource, which is the CPU. So how do we do that? There is a lot of math involved in how we do concurrency. It relates to the queuing theory and to Little's law, and it basically means that something equals something times something. It is too complicated to discuss in this talk, but I highly encourage you to take a weekend and read about it. For the purpose of this talk, we say that it is math and sort of E equals MC squared. That's the math behind that. Now let's try to get some kind of an intuition. So we have our task, get bid. And let's suppose that it is alternating 50% of the time in blocking state and 50% time in running state. We have a machine with 32 core CPU, hence we probably need to run 64 concurrent users or concurrent requests in order to utilize the machine. This is not the exact number, but this is the intuition. However, if 99% of the time the thread is blocked, the request is blocked, we probably need over 3,000 concurrent requests in order to utilize the CPU. And if it's 99.9, then we need over 32,000. And if we're using this scheme and we have fan out of 5, then probably we need over 150 threads in order to support this. And why is it problematic? Before I say why is it problematic, I will mention the C1M problem, which is a very well-known problem that we want to create a server that is able to support 1 million users. WhatsApp solved it a few years ago, and it's definitely doable. And we want to be able to build such servers in Java without a lot of friction. So, what are the problems with the current model that I have described? Every request needs one thread, and even more than one. A thread needs a stack. A stack is of size 1 megabyte. Also, scheduling between threads and replacing them and context switching is very heavy. It requires the operating system. It requires kernel mode code. In addition, launching new thread is also very expensive and even problematic. So it seems like there is a limit on the number of threads a machine can support, and it's around a few thousand to 10,000, but you can never reach 100,000. That's something that is not doable. So you are actually limited in the level of concurrency that you can achieve, and as a result, not able to use your hardware properly. So how do we solve it until now? We use the asynchronous mode, the asynchronous programming style, which means callbacks, non-blocking, event loop. We put event in a loop and then we could have a callback and it comes back to the event loop. And actually in Java it looks like this because we can use more than one thread at a time. So we have a thread pool that is handling the event loop. The most popular framework to do this kind of programming is called Netty, and while it is extremely powerful, it is also very hard to write code and to reason about the code that in this system. The code is less readable. If anyone saw callback hell in JavaScript, definitely know about it, but even if you use promises and completable futures, and composing requests one on top of the other, it is very complex and not easy to understand to most developers. In addition, the fact that you're breaking up everything to pieces and you have different fragments of running that are not connected to your main flow makes debugging, profiling, and troubleshooting a nightmare. Most of the tools that we have for the JVM, such as debuggers and profilers, and even logging and transaction tracing are failing when it comes to async programming. Another problem of this model is that it is viral. Because you have very limited amount of thread and they are relying on the fact that the code is not blocking, whenever you introduce blocking code into this mechanism, you break it up totally. It means that you need to replace everything. You need to replace your database drivers, your HTTP connectors, everything needs to be asynchronous and non-blocking. And if you make one little small mistake, you're done. And everyone that have done async programming probably bumped into this problem that a single synchronized code or something that blocks the thread kills everything. So we have two options, and this slide is taken from Ron Spressler talk. Either to work synchronously and have developer productivity and for certain use cases, very low utilization of the hardware, or have async programming where developer will be miserable and hardware will be fully utilized. And this is exactly what Project Loom tries to solve. It doesn't improve performance, but it improves developer productivity and sanity as a result, and makes everything much easier than before. So, what is Project Loom? The first JEP is JEP 425, which introduces virtual threads. It's currently in preview mode, which means it's part of the JDK, part of JDK 19. It can still have some minor changes in the future, but generally speaking, it is ready and looking for your feedback. A virtual thread is a unit of execution which can run on a carrier or platform thread. Threads, as we know them, still exist in the JVM, and introduced another construct that is called a virtual thread. How do we create a virtual thread? This is the hello world. Thread class has now a builder function that's called a virtual. You can give it a name, and then you call the start method and give it a closure. Okay, that's the way you do closure in Kotlin. To the closure, you introduce a runnable, and then it runs inside a thread pool. When it's finished, you can wait for it using join. But usually in our programs, we don't create threads. We are told that it is a very bad idea. That's why there is another form of executor that you can use in order to utilize the virtual threads framework. So you can use the new virtual thread per task executor, and it complies with the same interface of executor. Now, executor in this version is also auto-closable. So you can apply try with resources, or in Kotlin, it's called use. You submit a callable, you get a future, and you are done. Okay? So everywhere in your program where you had an executor, replace it with this one, and we work on virtual thread instead of threads. Not in all of the cases, it is useful to do it. How it works behind the scenes. So we have a lot of virtual threads in our system. Some of them are in blocked state, and some of them are in runnable state. In the JVM, there is implemented a scheduler. This scheduler relies on a bunch of platform threads that are called the common pool. And whenever you want to schedule, or the scheduler wants to schedule a thread, a virtual thread, to run on the common pool, it calls something that's called continuation run, mounts the thread into the carrier thread, copy the stack into the stack of the carrier thread, and run it. Whenever the virtual thread gets into blocking I/O, it will yield and be unmounted back to the pool of virtual threads. Okay? And another thread, virtual thread, will be scheduled into the common pool. What about stack? Stack frames of virtual threads are part of the carrier thread when they are mounted, and they are held in the heap when it is unmounted. And what's nice about it is that the amount of memory a virtual thread consumes on the heap is very low, much, much lower than a regular thread. In this example, you can see that 100,000 threads consume 15 megabytes of memory in my JVM, which is very low. And also, you pay as you go. As the stack trace grows, the memory grows, but initially it is almost zero. So Loom has two parts. The first is changes in the JVM. They're relatively minor, mostly mounting and unmounting threads and copying the stack trace back and forth, and some changes to the garbage collector in order to support changes in GC root scanning. Most of the changes are part of the JRE, so the libraries are changed, introducing continuation and changing basically every blocking I/O operation that you have in the system, including thread.sleep, okay, which is not I/O, but it is blocking. And it changes it to use in case it has a virtual thread. It using continuation and yield instead of the park method that we got used to when the thread is parked. And virtual thread try to imitate every behavior that a regular thread has. This includes something that is very important that is called thread lockers. So if you have developed in ASIC mode, you probably know that you lost thread lockers. And if you need some context or moving things between operations, you need to do it yourself. Virtual threads support thread locker, and they actually populate from the calling thread to the new virtual thread if they are inheritable, okay? So if you have some kind of a context in MDC or in thread local, such some kind of transaction ID or something like that, and the thread local is inheritable, it will be copied to the virtual thread. It has some overhead, so if you want to not use it, there is a flag that I will show in a minute, but you need to take into account that all the other usages of thread lockers are meaningless with virtual threads. In some cases, you use thread lockers to hold some kind of very hard to compute cache, or maybe even something that is not thread safe, like an XML parser that is very hard to construct. It doesn't make sense for virtual threads because virtual threads are very temporary. They are destroyed the minute you finish the task. So if you want the thread local not to be populated to the virtual thread, you apply the method inherit, inheritable thread lockers to be false. Now let's talk a bit about structured concurrency, which is JAP 428. Structured concurrency is in status incubating. It means that it is part of the JDK, but if you're using it, prepare for it to be changed in the future. It's not fully final. And the purpose of structured concurrency is to make writing correct concurrent code easier with the support built in for cancellation, error propagation, and timeouts. In addition, it enables us to observe hierarchy of virtual threads at runtime, and I will discuss it a bit later. So if we go back to our example that used concurrency, how will it look like in structured concurrency? So first we find the user by email, no change here. Then we create a scope. And the scope is also auto-closable, so you try with resources or use in Kotlin. Then you fork and give each fork a callable, which you can collect later on. And then you join the scope. And when you join, it means that the scope is handling all what is needed in order to complete everything. And if things didn't end at time, they will cancel it and do all the heavy lifting and will make you, by the time the scope is closed, everything should be terminated and interrupted. So it seems a bit nicer. And when the examples grow more complicated, the benefits of this structure make sense more and more. So this is structured concurrency. It also supports, of course, you can have timeout in the join. You can join until, but it's very nice. It's something that you should definitely use in the future. What about tooling? So virtual threads are very harmonious with the toolset and toolchain that you have in your JDK. So you can put a breakpoint inside the virtual thread. When you're using IntelliJ, you can watch the stack trace of the virtual thread. And you can even see all the rest of the virtual thread, even the ones that are not mounted inside your IDE. So you are able to track and understand what's going on here. JStack does not support virtual threads because it's not scalable enough to support it, so you always show platform thread in it. But you can still dump the virtual threads by using jcommand thread dump to file. In this case, it will dump platform thread, structured concurrency, and also tasks that are submitted to executors. It will not show the basic the creation of new virtual thread inside this thread dump. What is also very nice about it is that if you're using structured concurrency, this tool is able to link between the stack trace of the parent thread and the child thread, which give it a very powerful mechanism to understand what's going on that is very missing with other concurrency constructs. Java flight recorders also support several new events inside of it. And I guess that is all. So let's summarize. Should I use Project Loom in production? Of course not. But maybe, if you're starting to write a new project that requires high level of concurrency, 100 or 1,000 concurrent users, you might be benefiting so much from this that you want to take the chances and use this preview mode. It will make your life easier. If you want to play around, definitely try Project Loom. It's very easy. I've created a project, Playground Loom, in my GitHub repository, and also Uri created one a few months ago. Very easy to start going on with it. And of course, if you want to provide feedback to the writer of Loom, that's the time. 6 months from now, it might be too late. Also, Jetty supports Project Loom. Since version 10.0.12, you can enable it by adding a simple change to the startup of Jetty server. GraalVM supports Project Loom. Quarkus supports Project Loom. And if you want, and even there is a project called Helidon, which have certain flavors of implementation. It's a microservices framework. The developers of it created a new Helidon server that is called Helidon Nima, based on Project Loom. And the amazing fact that very easily they got to the same performance that you get with Netty, okay? And the author of it wrote that we've dumped synchronous code on Loom and some simple tuning quickly got to similar or better performance to Netty. This is mind-blowing. So if you really want to start, you first need to use JDK 19 with the flag enable preview, otherwise it will not work. If you want to use structured concurrency, you will also need to add the module incubate or concurrent. And there are two things that you need to remember if you are using it in production. First of all, there is currently a limitation. If you're using synchronizing the code, reentrant lock is okay, but synchronize will pin the thread through the synchronization block. It will not be able to unmount. So if you have a synchronized block that is doing I/O inside, it will get stuck and the thread will not be able to be unmount. And this might be a problem. You can monitor it, you can understand what's happening. Usually it's not a huge problem, but definitely need something that you need to think about when you're using it. It will be probably solved in the future. And the last thing I want to say is, remember, threads are expensive. Virtual threads are very cheap. As a result, you should never pull them. Always create a new virtual thread, use it, throw it to the garbage, take a new one. Pulling virtual thread is not the right way to go. So this is the end. I highly recommend for you to watch talks about Project Loom from Devox. There are ones by Ron Pressler and two others that are very good. And I really thank you for your time. And if you have questions, you're welcome to talk to me later or Discord channel.